Okay, no.
Alrighty, hi everyone. Welcome to last minute review for tonight. I have a question in the chat about work efficiency, or I'm sorry, about efficiency and reversibility and what delta G looks like in that sense and whatever. So I'll start there, but if you have any other questions in the meantime, feel free to put them in the chat, or just when I'm done with this one, we can talk about, you can just take yourself off mute and ask them. But this time is yours, so any questions that you might have, we can go over them, and we have an hour, so get started. So basically the question is just talking about the relationship between reversibility and efficiency of a reaction and what delta G would look like. So just as like a quick recap, delta G naught is going to be your free energy. When delta G is equal to 0, we're at equilibrium. Right, so you're going in the forward and reverse direction. If delta G naught is less than 0, we have an exergonic reaction. And if delta G naught is greater than 0, then we have an endergonic reaction. Okay, exergonic is preferred by the universe. We would like we would like energy to be released, this free energy to be released. But at 0, we're going to be at equilibrium. And when we're at 0, we're at the special case of delta G, where it's equal to 0, this is where we have the most reversible reaction. So when the closer you get to equilibrium, the more reversible the reversible, is that the word I'm looking for? Yeah, the more reversible the reaction can be, right? And this makes sense because if you're having equilibrium, you have the forward direction and the reverse direction happening at equal and opposite times. So the closer you get to the closer you get to equilibrium, the easier it will be for the forward or reverse reaction to happen. If we're at a case where delta G is equal to, let's say, negative 500 kilojoules, right? We're a little bit farther away from equilibrium at this point. And say delta G was negative 15 kilojoules, right? At negative 15, we now have a little bit closer to 0 compared to negative 500. So the negative 15 reaction is going to be more reversible because we're closer to that equilibrium portion. Does that make sense for reversibility of a reaction and what that does for delta G? Are there any questions on reversibility of delta G? Right, you can just think about right, delta G being 0, equilibrium. What does equilibrium mean? That means forward and reverse is happening. So if both reactions are happening, then it's going to be easier to reverse the reaction that happened. Alrighty, what other questions do we have? Yes, very spontaneous reactions are not very reversible. So if you have something that is like negative 3 trillion, right? That's going to be really hard to reverse because a lot of free energy is being released. And it's hard to regain all of that free energy to make the forward reaction happen. Yep, so there was a follow-up question for that, and it said those reactions would be efficient, but the free energy is not usable for work, and that is correct. You are welcome. Anything else we want to discuss? Any questions on the homework, practice questions? Do. I think y'all seem a little more confident on this exam than the couple previous ones. Do we want additional practice? Do we just want to hang up? What's the vibe? This is your time. Yep, so I had a question about the delta E equation. So in your notes, I believe it's delta E is Q minus W, or maybe Dr. Lindahl talked about that in class. But then I showed delta E is equal to Q plus W. It does not really matter which version you use, as long as you as long as you have the appropriate signs for system versus surroundings. So if you have something where work is being done on the system by the surroundings, would that be a W negative or W positive? Yes, this would be a positive W. So if work is being done on the surroundings by the system, right, opposite of what this of the first one was, this would be a negative W. So if you put this into your delta E equation, delta E here would be Q plus W, right? It would be plus positive W for the first one, or delta E would be Q plus negative W for the second one. So it would result in Q plus W or Q minus W. So it just depends on how work is being done, whether it's on the system or by the system. I like positive numbers, so I tend to use the plus W, and then I just change it depending on how work is happening. Yep. In terms of like this equation here, sometimes you'll see Q and sometimes you'll also see delta H of reaction. Those are the same. So this could be delta E is equal to H of the reaction plus W, and that is totally fine. Right, if delta H was negative, right, if they're saying that the reaction has a delta H of negative 25, then you're going to plug in negative 25 here. But if the reaction has a positive 25, then you're going to put positive 25 there. The reaction is always your system. And so if you define it by the system for delta E is equal to Q plus W, then that will tell you if it should just be negative or positive. Usually that's given to you in the question, or you're going to solve for it. So I think delta H is a little bit easier to understand rather than work. What other questions do we have? Absolutely. Okay. So for question 10, right, we're going to still consider these all just true false questions and see what sticks, essentially. So for statement 1, we said if delta naught reaction is positive, but delta G reaction is negative for a reaction under particular conditions, the reaction will occur spontaneously under those conditions. So how this reads is saying your standard conditions is positive, but these non-standard conditions are negative. So under those conditions that it's talking about are the non-standard conditions. So if delta G is negative under those non-standard conditions, will it be spontaneous or not spontaneous? Yep. So this would be spontaneous and right, occur spontaneously, that matches up. And so this would be a true statement. Okay. Gilbert Lewis was one of the founders of statistical thermodynamics. Is that true or false? Was Lewis the one that did thermo? Nope, he was not. Yep, so you can change this statement in two ways in order to make it true. So you can get rid of Lewis, and this is actually going to be Boltzmann. Was the one of the founders of thermodynamics. Or you could keep Gilbert the same, and he was one of the founders of covalent bonds and like electron theory stuff. Okay, so this one is not true. Oh, time for bed. And then 3, without exception, state functions are pathway independent. Is that true or false? Were there other ones for statistical thermodynamics or covalent bond theory? For founders of statistical thermo, I think there were probably others, but I think the main one is Boltzmann that you need to know. I can't remember if someone else is mentioned in the notes off the top of my head, but Boltzmann is really the main founder guy that I think he would ask you about. So I think if you, as long as you know Boltzmann, you should be fine. Okay, and then just to finish up question 10, without exception, state functions are pathway independent. Is that going to be true or false? Yes, this is true. It doesn't matter what pathway you take, it will always be independent, right? It doesn't matter if you think about potential energy, right? It doesn't matter how you push something off a cliff and which way it falls off the cliff. It will have certain potential energy at the top and certain potential energy at the bottom. Those are all state functions, so this is true. And so B is going to be your correct choice, with A and B both being, or with 1 and 3 both being correct. Yep, everything is a state function except heat and work. Right, like delta G, delta H, delta S, those are all pathway independent or state functions. But work and heat are path dependent. And then I have a question about question 10. So for statement 3, we're saying a macro state is a very large state of the system. So the question was saying, why is this false? Right. They thought that macroscopic was energy related properties of an entire ensemble of molecules. And that's correct. Right. We think of macro states as like the pressure of the system, the temperature, all of these big components of it. but I think how he was saying this is that he's literally saying macro is very large, right? You're just taking a very large portion. He's being very literal with this. He would say, I think if he was trying to say that a macro state to be true, it would be defined as a macro state is a energy related property such as temperature of an ensemble of molecules. I think he would make it more narrow in terms of the definition rather than this broad, large state of the system, I think is what he was going for here. And so that's why it would be false. So your definition is correct. So still think of it that way, but I think he would just use more of that definition if he wanted it to be true. Yeah, or something related to statistics, right? He would use more language, I think, if he wanted it to be a true statement. I think this one, he just was being very literal for what macro meant. With my eyes back. What else do we got? Feeling good? Feeling confident? Adrian, not to call you out, but did you figure out practice 5 from the notes?
Yeah, he kind of went over it in the review session. He didn't have the numbers, so I had to tell it to him. So I don't know if he got it completely right. I mean, he
Okay.
didn't get the right answer, but basically what he did was we found what delta S would have been, and then you just multiply it by the amount of moles. So since it's almost 2, you'd multiply it by 2 and you should get around 249. But when we did it in class, we didn't get it. So I don't know.
um
He said not to really worry about it.
yeah,
So
I think it should be okay. I don't remember what the other answer was that I tried. I think it was like 138 or something. Yeah, I think it's pretty close. Yeah, you understand the concept, so I think you're fine. I think you'll ask different questions on the exam anyways. I have not seen the exam, so I don't know what it looks like. But if he tells you not to worry about it, you should be fine. Okay. Okay, so that's a really good question. So I had a question about delta G and delta G naught. So whenever we're looking at a question, we can have delta G naught of a reaction or delta G reaction. This naught here tells you you're at standard temperature and pressure. If it doesn't have the naught, then it's not at standard temperature and pressure. And standard STP, right, is going to be 25 degrees Celsius or 1 atmosphere. And 1 atmosphere. So if you're not at 25 degrees Celsius, you're going to be at that just delta G of reaction. If we're talking about spontaneity, what makes something spontaneous, it doesn't matter if it's delta G naught or delta G, right? And that kind of relates to question 10 here. Well, right, delta G naught is positive. So here, this is non-spontaneous. But at some other temperature, it's now negative. So this is spontaneous. So at that new temperature, we now have a spontaneous reaction. So this is like one of those conditional statements, right? Where it's like, okay, maybe at a higher temperature, we get a spontaneous reaction or at a lower temperature, we get a spontaneous reaction, but it wouldn't always be spontaneous, right? Has some condition of when it's spontaneous and when it's not spontaneous. But in order for it to be spontaneous, at least one thing of delta G, whether that's delta G of the reaction or delta G naught, has to be negative, and then it could be a spontaneous reaction under those conditions. Seriously, take a shot every time I say spontaneous and you'll be good to go. Does that make sense? How spontaneity and delta G relate to each other and the difference between delta G and delta G naught? Okay. Right, it's kind of, if we think about the 4 conditions of delta G, right, you can have, right, it's always less than 0. And that's when delta H is negative and delta S is positive. We can have delta G is greater than 0, and that's non-spontaneous. And that's when delta H is positive. And delta S is negative. And then we can have our conditionals. And this is when delta H is positive and delta S is positive, or delta H is negative and delta S is negative. At low temps, their first one will be spontaneous, and at high temps, your second one will be spontaneous. I so lied, that's the opposite. Sorry. Did I just write? It's past my bedtime, y'all. This is high temp. This is low temp. Spontaneous. Okay, that clear up delta G and everything. Any other questions?
I don't really know how to write this out, so I'll just explain it. So he gave like an example where like if he gives us an equation or a formula, yeah, just an equation, whatever. And it's the reverse of like a KSP dissociation. We know that we need to take the inverse of KSP to use it in our formula.
Okay.
And what condition, I know like if he were to give us initially, then that equation where the coefficients are all doubled, then you would also have to square the KSP, right?
Yes.
What would be the situation where you would have to raise it to like the half power, if that is even possible?
Yep. So when we're looking at K values, right, if we have a KSP, this is saying some insoluble salt, we'll say silver chloride is solid. This would go into Ag plus and Cl minus. Okay, those are both aqueous, and that's a reversible reaction. So your KSP for this would be Ag plus and Cl minus. Okay, the reverse of that would be if Ag plus and Cl minus form AgCl solid. Now your KSP is not necessarily KSP because it's the solubility product. Now your K nu, we'll call it, is 1 over Ag plus times Cl minus, because we're not going to include that solid. So to go from KSP to K nu, we had to do KSP to the -1 power. Okay. In a similar sense, right, if we just had a generic reaction where we had A plus B is reversible with C plus D, if we wanted to get to 2A plus 2B goes to 2C plus 2D. I should have picked less letters, but right, K here is C, D, A, B. Now K1, we'll call this one, is C2, D2, A2. So this one is now K is equal to K1 when you square this. If you wanted to go from 1 to 2, you could also say K1 to the 1/2, not to the negative, sorry, to the 1/2 is equal to K. Because now you're just dividing by 2.
All right, but I guess in like practice, you probably wouldn't go from a given KSP or KA or something of the sort to a lesser coefficient in a sense.
I don't think so. I think most of the time it's given to you in its simplest form already. And you're not really going to reduce it further. I think that one's just more of like conceptually, if he asks you a question about it, you would have to do the 1/2. Most often you're either just flipping it and have to take the -1, or you have to multiply it by 2 or 3 or something. So you're generally going to work with a negative exponent or a positive exponent, but not a fraction.
All right, thank you.
Yep. I'm not entirely sure of what the question would ask in terms of trying to, right, so the question is, how do we know to take the inverse? What would the question look for? I'm not sure how we would actually ask it, but if you're given a KSP, right, we know KSP is the dissociation. Right, so that things breaking apart. If your reaction is showing something forming, right, if we have something where A plus B forms AB, right, we're forming something that's not a dissociation, that's the opposite of a dissociation, that's an association. So using context clues, we would need to say, okay, this is the opposite of what the dissociation would be. It might also say something along the lines of like, a solid is formed or ions come together, right? Some sort of fusing verbiage in order to indicate that something is being formed rather than something is being broken apart or dissolving.
I think practice problem 1 in the lecture has us flip the KSP.
Let me look at that.
At least in our lecture, that's what led to the conversation of doubling and all that stuff.
Yep. So, right. Dang, it's like I know him. He also uses silver chloride, right? So it's saying KSP for AgCl solid is this at 25 degrees Celsius. And so we're looking to find delta G naught of the reaction for the reaction So right here is an indicator where we're given KSP, we're given a dissociation constant, but this is a forming or an association reaction, right? So if we were to write out what the KSP would be, it would be silver forming or silver chloride forming silver ions in chlorine ions. Since we know we're at equilibrium, we need to know that we can use the equation delta G naught reaction is equal to negative RT ln K EQ. But it's not KSP directly because we're looking for the reverse reaction, that formation of silver chloride ions. So we need to take the inverse, or 1 over 1 times 10, 1.8, excuse me, in our equation because we're looking for the formation of chlorine ions and not using the dissociation of chlorine ions. That's right, we're looking for the formation of silver chloride, not the dissociation of silver chloride. Does that help a little bit of what they would ask for in order to flip it? Right, KSP is things breaking apart. If you want to use it in the reaction, it's probably going to be forming together, and that's going to be when you have to flip it. Good. Good questions. Anything else? Feel good? Feel great?
Did you talk about the second law of thermo and like specifically his slide 16? Can I just explain it again real quick?
Let me just pull it up. Yes. Okay. So for the second law of thermo, we are saying that the delta S of the universe is always increasing, right? There's always going to be more disorder in the universe. No matter what happens, you will always have more chaos as a result. We also know that the delta S of the universe will equal the delta S of the system plus the delta S of the surroundings. Right? Because everything is equal and opposite. If something is getting work done on the system, that means that something had to be doing work. If something was gaining heat, that means that something has to be losing heat. Okay, so if the S of the universe is greater than 0, and the S of the universe equals the delta S of the system plus the delta S of the surroundings, we could say that delta S of the system plus delta S of the surroundings has to be greater than 0. Okay, which means that there are 3 different cases that can happen, right? Think about how we have delta G. We have 4 scenarios that can happen where it's always spontaneous, non-spontaneous, spontaneous at high temps, or spontaneous at low temps, right? We have 4 conditions for delta G. For delta S, we have 3. all relating back to this idea that the universe entropy always has to be increasing. So you can have delta S of the system and the delta S of the surroundings can both be greater than 0, right? Both of those can be getting more chaotic, and therefore the universe is increasing because that upholds that system, or that holds that statement. You can have delta S of the system is getting smaller, right? It's less than 0, but now the delta S of the surroundings is greater than 0, and it's larger than the difference that the system got smaller, right? So if this is going down by -10, this might be +15. So now the surroundings is getting even more chaotic and offsetting that less chaoticness of the system, therefore still contributing to the universe entropy. And then the reverse can happen where delta S of the system can be greater than 0 and delta S of the surroundings could be less than 0. But then in this case, the system would be gaining more chaos than the surroundings was losing. Does that clear up that slide a little bit?
So basically the net just needs to be positive.
Yep, net positive entropy. Things can have negative entropy, right? You can get less disordered, but that means that something else got even more chaotic than something that got disordered, that got ordered.
Is that how we're still like a negative entropy organism because we're eating all that stuff? Or is that a different concept?
Yeah, I believe so. Right, but and to finish off that slide, right, you can't have both of those things getting less negative or getting more disordered, more ordered, because then you would be taking away delta S of the universe. And that can happen.
So that can or can't?
It cannot. No.
Yeah.
What else do we got? Did the practice exam feel good this time around? Feel a little bit more confident with this one? Mhm. Yeah, I think there's a good comprehensive list. Yeah. So here are some important equations. So I would ask you, but it's hard to write these, right? So we know that delta S of the universe we just talked about is greater than 0, right? This is the second law of thermodynamics. And S of the universe is equal to delta S of the system plus delta S of the surroundings. Okay, you have your Boltzmann equation, which is delta S is equal to K, which is a constant that's given to you, times the ln of W final over W initial. And these are your state functions at the beginning and end of the reaction. If something has more microstates at the end than at the beginning, then you're increasing entropy, pardon my yawn. And if you have less microstates at the end at the beginning, then you would be losing entropy, right? And microstates relate to the entropy of the system. So the more microstates you have, the more disorder you have. Okay, you have how to find delta S of the reaction. And this is your sum, right? Where you have N times S naught of the products, the sum of this, plus the sum of the number of moles times S naught of the reactants. Sorry, not plus, minus. So you want to sum up all of your products and multiply by any coefficients they have, and then subtract that from the sum of any reactants and any coefficients they have. This is the same how you find delta H and delta G if you're given standard enthalpies, entropies, delta Gs for this. It is always products minus reactants, and it's the sum of the products times their coefficients minus the reactants, the sum of the reactants times their coefficients. Things above 0 degrees Kelvin will always have some sort of entropy with them, so you probably shouldn't ever have a 0 that you're plugging in for delta S, but you can have a 0 for delta H because your standard enthalpy of formation for its natural state will always be 0. So can have zeros in delta H, can't have zeros in delta S. Okay, I think the big one here is delta G naught of the reaction is equal to delta H naught of the reaction minus T delta S. We have solving for non-standard conditions, so if delta X of the reaction is delta G naught reaction plus RT ln Q, right? This is not at equilibrium, which is why we're using Q here. But then if we are at equilibrium, we can use RT ln of KEQ, and that's that equilibrium constant. And I think those are the big ones you're going to use. I think it's really the big ones I've seen throughout the whole practice exam.
The other one where you combine those two last equations, wherever in the end it will be ln and q over keq.
Yep, so you could also write this is this. So you could say delta G reaction is equal to negative RT ln of KEQ plus RT ln Q. So then, right, you take out the RT, and then it's minus ln KEQ plus ln of Q. I think that's what it is.
Yeah.
Alrighty, anything else? Alrighty. Well, if there is nothing else that y'all have questions on, I can let you go a couple minutes early. I'll post this as soon as possible. I low-key might fall asleep and I'll do it in the morning. But if I'm still awake when I get the Zoom recording back, I will post it. But if not, have a very nice night. Good luck tomorrow. I will see you there. I will be hobbling around, so just bear with me if you have a question. And I'll have my phone available for most of the morning. So if you have any last minute questions, feel free to email me. But good luck and make sure you go to bed and get a good night's rest and have a great night. I'll see you tomorrow. I'll hang around for a couple minutes in case anyone else has any questions. But good night.